You know how the introduction is very important. So you have to understand the introduction in order to be able to go deep into this topic with clear understanding. Just remind us, what were you able to pick from the previous lesson? Just put up your hand as we wait for the people who are coming in. Akelo, your hand is still up. I don't know if it is still under the same concern of telling us what you went through. Kasacha Joy, may you remind us, unmute and remind us. Joy, unmute.
Teacher, we talked about how to find the resultant, how to get the resultant force, the center of gravity on both the regular bodies and irregular bodies.
Pick out one concept and tell us about it. Just one.
Okay, that's what we talked about.
That's like you are summarizing what we went through. Anything particular?
For the regular body. Okay, when we talk about the regular bodies, we can use balancing, and there we can use the meta ruler, and the center of gravity is the middle point while we're balancing.
So if the meta rule is about 50 centimeters, where will the center of gravity be?
25.
Wonderful, thank you so much. Another person, what did you pick? Quickly before we get to the next concept. Okay, Daniela, Cynthia, Tyler, unmute and submit.
I learned that there are different atoms that make up a body, and they all have different weights. So to get the total weight, you have to find the center of gravity.
Wonderful, thank you so much. So the center of gravity, okay, I need a definition, because what you're saying really takes us to the definition of center of gravity. Let's get someone to give us that. People, use your full names and include your streams. Tani, Gabs, we really get to believe that you're not a student, though your hand is up. Just use your full names and your stream. Okay, Akelo, your hand has been up. May you unmute and submit.
The center of gravity of a body is defined as a point of application of a resultant force due to the Earth's attraction on it.
Exactly. Thank you so much. The center, the point of attraction of the resultant force on a body due to the Earth's attraction on it. Wow, that's a very excellent definition. Okay, we have Angel in Tongo, unmute and submit. Angel?
Teacher, we looked at how to find the center of gravity in the irregular lamina.
May you quickly summarize what we were able to do?
Okay. You get the lamina, and then you make 3 different holes, and then you balance it with the how is it called? The plumb and a string, and then you keep on making different points where the hole you've made and crosses the center of the lamina to the point where the string makes when you, what is it called? When you suspend it.
Yes.
When you suspend it, and you keep on making the lines, and then the center of those lines is the center of gravity.
Repeat that. Repeat the last statement.
You make 3 holes, and then you make 3 holes, and then you label them.
What happens
in
the line?
The last thing about the lines, just the first thing is okay. The last thing. What you do with the lines?
The lines, when you make the lines, the center of those lines where they pass through the lamina to go to wherever they are going, that center where they all meet at some point is the center.
Where they meet.
The point where they intersect or they meet in the center of gravity.
So that is the statement, the word you were looking at.
Who was that one? Tendo?
It was Angel in Tongo.
Angel.
Angel in Tongo. Ancient Togo, you have described that experiment lightly, and I want to caution girls, don't take that question lightly. It is the most frequently asked question, locating the center of gravity of an irregular lamina. So we must get the language correct. Please, whoever is relaxing, you have some time, take time off and make sure that you really understand to go how to describe that experiment. However, if I'm using memory, really, that was good memorizing. And I think you try to understand. Now it would be far much better if you really went through it and described the experiment properly. So girls, I'm cautioning you, take that experiment seriously. Okay? Briefly, I think most of the things we wanted to discuss about are being discussed. Now, I want to point out something about the center of gravity of a irregular body. Can somebody tell us where we locate the center of gravity of a regular body? Somebody tell us in brief, just using where do we find the center of gravity of a regular body?
Okay, you can see Talita, Sarah, 2S, unmute and submit.
Okay, teacher, when you draw the diagonal lines where they meet.
That the center of gravity of a regular body is found at this point. That's how I want you to answer the question.
The center of gravity of a regular body is found at the point where the diagonals meet.
Okay, that's for a rectangular lamina.
Generally,
if you had a uniform meter rule,
where
a uniform lamina,
center of gravity.
What can you conclude about the center of gravity for those regular bodies?
This one is
okay. We have Nisima Daniela. Maybe you supplement on what Sarah, what you said was okay. There you concentrate only on one body type of regular body. Okay, we have someone here
is
called
Naomi. Is it
Melima Daniela? Unmute and submit.
The center of gravity for regular bodies is usually at the center of the regular body.
Very good. Also, the center of gravity of regular bodies is found in the middle or the center of the body. So those regular bodies, we are now going to use another word. They are also called uniform, a uniform body. We are going to come across that word regularly. So instead of where we have the word regular, we shall be using the word uniform body, a uniform body. The moment you hear that body, that a body is being defined as uniform, they are giving you information that the center of gravity is always at its middle point. That's why Mr. Sally asked you that where do you find the center of gravity of a uniform ruler? Our uniform ruler is 100 centimeters. So what is the location of the center of gravity? Around that point.
Okay, I can see someone ready to give us an answer. Walea Mercy, unmute and submit.
Teacher,
Walea, be with us in the lesson. Otandeka Laura, may you respond to Mr. Sanjeva's question?
It's 50. The center of gravity is found at 50 centimeters.
Exactly, it is found at 50 centimeters. Is that okay? So whenever we are given uniform bodies, and in most cases, most of the uniform bodies we are going to be talking about are rulers in most cases. Or in a beam, they'll give you the length, and automatically, the moment they use the word uniform, you will know that its center of gravity is at the midpoint. Is that clear, girls?
Yes.
Yes.
And a conclusion on Mr. Sanjeva's submission, where the center of gravity is where the weight or the mass of that body appears to concentrate from. So we shall always locate that point to be the point where the mass or the weight of that body is, especially when we are working out like we are going to see in today's lesson. All right, let's proceed from where we stopped last time. You just tap on Mr. Sanjeva's window, you see the notes shared on the screen. So we stopped on the note. Someone read for us that note very fast, and then we progress I want to give someone who hasn't said anything. Priscilla, unmute and read for us that paragraph of note.
Sanyu Priscilla.
Note, in the laboratory, the plum can be replaced by a pendulum bob. Secondly, the center of gravity of a body does not always lie within the material. It may also be at a point in space nearby. The best examples are a tripod and a laboratory stool.
Thank you so much, Sanyu. So what we use as a pendulum bob, that was a string with a metallic ball. That was a pendulum bob. So, but practically, we use a plum. Okay, so we just replace it and use that so to can access. Now, this brings us to what always people refer to as moments. People always call this topic moments, but the actual one is turning effect of a force, which is also interpreted as moment of a force. And that's where we want us to start from, moment of a force. In today's lesson, Mr. Sanjay, would you love to introduce us to this?
Okay.
Let Mr. Sanjay take us to the introduction, then I will come in.
Good morning once again. I want us to look at the turning point, but from a practical aspect. If you are close to a window or you are close to a door, I want you to look at the placement of the handle and the hinges. And then, I'm asking you to observe first before you comment. You obey this rule. Don't be quick to talk, be quick to listen, okay? So listen first and then you comment. So we are talking about, look at the placement of the handle in relation to the hinges or the turning point of a door or a window. So having looked at that, make an observation and give it to us quickly. I want a person who has made that observation where the handle is rotated and then the hinges.
Okay, Shona Lugolo. Lugolo Shona, your microphone is open. May you submit?
Yes, the hinges, I think they are attached to the wall, and then the door is, like, the handle is attached to the door. So when you open it, the hinges turn, and then as you close it, they also turn as well. And as well as the knob of the door.
Okay, that is a submission. Anybody else who can make another submission?
Okay, let's see someone. Sincere Nachigude, unmute and submit.
When you open a door using the handle is moving downwards.
Okay. Another submission.
Namuli Nicole, unmute and submit.
Sorry, I left my hand up by mistake.
Okay. Let's see. Amuna Chloe, unmute and submit.
Teacher, they are at opposite directions. Like you can't find the handle and like the place where you open from at the same position. So they're like opposite.
Okay,
that's a very good observation.
That is one of the observations that we want to make. In most cases, the hinges and the handle are at extreme ends of the door or the window. If you look, you will always find the handle at the extreme end of the hinges. It is as far as away as possible. Is that okay? That is the first observation I want us to make. Number two, where do you apply the force to open the door or the window? Where do you apply the force to open a door or a window?
The handle.
The handle. Now, when you apply that force, what happens to the door?
It moves.
It unlocks and then
moves inwards or outwards.
And how? What is that movement called? What is basically happening? Use the words that you see now in the notes. It moves.
How does it move? Does it get out of?
Clockwise or
Clockwise.
No, look
I
at the
think it's
one.
anti-clockwise.
It does what?
It moves about the hinge.
What is the title of our topic?
Turning.
Turning effect
It
of a
turns.
force.
It
Turns.
turns. Is that okay?
Yes.
By a force, the door will turn, and it turns about what point?
What point? The fulcrum.
The fulcrum. So you are naming the points that you are talking about. Your point. What is the other name for fulcrum?
Pivot.
Pivot.
Is that okay? Now, you also discovered something. Suppose you are on a seesaw. You know what a seesaw is. I hope you went to nursery school where there are seesaws.
Yes.
Yes.
Somebody heavy and somebody who is light. Who sits near the keyboard?
Which is the one who's heavy.
The person who is heavy.
The person who is heavy sits
The
near
one
the
who's
keyboard.
heavy.
Very good. I think now we are ready to go through the turning effect of a force. Because we have some examples, isn't it?
Yes.
Okay, but before you tell me other turning effects, we have talked about the door and the window. Can you give me other examples where turning is important? Look at the things in your house which you turn
Teacher.
apart from the door and the window.
Teacher, when you're opening the container.
A container, very beautiful.
When you're opening
So when the blender is blending.
When you're opening a padlock.
Okay, that is okay. You have ever used a screwdriver?
If you're opening a tap.
Have you ever used a screwdriver?
Yes.
Have you ever been in a car?
Yes.
There. What turns in the car? You are inside the car. What is that thing that you turn in a car?
A wheel. Steering wheel.
Steering wheel.
Okay, so we have realized that we need to study turning effects because they are quite important in life. There are so many things that we turn in life. Have you realized that you have several examples?
Yes.
Okay, so now pay attention to these applications and the physics explanation for what you see in your life. Are we together?
Yes.
Mr. Sari, please.
Okay, thank you, Mr. Sanjoy, for that very practical introduction to this. Now, someone will read us for us that paragraph under our title, Turning Effect of a Force, such that now we get to the... Yes, please go on.
A force has to be applied to a machine for it to work. It's important to know where the force should be applied for the machine to be more efficient in doing work. In this chapter, we are going to study the turning effect of a force.
All right, so let's quickly get to that experiment. We are going to investigate the turning effect of a force. The turning effect of a force. I believe people can see me. I have a wooden block. All these things, we'll try them out when we come back to school. So you tap on my screen, let me answer. You want to understand what a clockwise turn is and an anti-clockwise turn. People have already talked about such directions when they are opening their doors, when they are opening and closing their doors. So let's just see what we need from that in physics. Okay. Let me unshare the screen such that you can see but you can just tap my camera or some symbols and then you'll see what we are going to do. So this is my wooden block and then this is my wedge. Okay, and then we have a meter rule. I'll use a half meter rule so that it can be seen in the screen very well. Okay, so now looking at this meter rule, let me adjust such that we can see. Okay, we want to, last time we balanced, being a uniform meter rule, it will balance at its center when you balance it, because that's where all its weight appears to concentrate from. It will balance at 25. So something like that. All right, now I want to see what we call a clockwise turn. I'll just use my duster, okay? I want to put this duster at that point. And then I'm also supporting this side such that it doesn't turn. But when I leave it to turn, if I remove my hand, where is it going to turn? Which direction is that? If I leave, where is this force turning the meter rule? Saying anti-clockwise. Is that what we are seeing from that side?
Yes.
Wonderful, okay. So that is what we call an anti-clockwise turn. Okay. And the moment, in this case, it's known as the anti-clockwise moment. And that is the diagram we are going to first draw in our notes, because whatever we understand, then we draw our notes. Let me try to make it. So that is the first diagram we are talking about. We are going to sketch it very fast, okay? So we have, you use a ruler while you're sketching. So we have a ruler, and you don't have to draw. I believe we are seeing the chalkboard. So that's all. I don't have really to draw a very big ruler. Then we have our turning points, and then we have a mass. Okay, let me first put a turning point. I believe you draw. People who wrote down the notes, you are filling in now these diagrams, okay? So we have a mass. Now this mass M1, it can be put there, or you can just hang it on a string. So this is our mass M1, what you have in the diagram there, okay? So that means its weight.
So Sally, please position the laptop better.
Please adjust, because you can't see the diagram.
Yeah.
Hi.
Okay, let's unshare and then we. All right. Is that okay now?
Better.
Yes.
Okay, so now this is the mass we have in the notes, okay? Mass M1, which I use as my duster. It's likely to turn the body in that direction, but what turns the body is the weight. The weight. So weight is drawn with a line, acting downwards, and an arrow. Okay, so you can draw, you know, weight always comes from the center of the body coming down. So we may have to do that such that we follow the principles. Weight always comes from the center, but we are locating it anywhere to represent this weight, okay? So how do we convert mass in kilograms to weight? Can someone remind us? How do we convert mass in kilograms to weight? Namala, your microphone is open. May you tell us? What will be the weight as a result of this mass M1? Okay, let's pick another. Namga Wodafin, unmute and submit.
Girls, don't miss the opportunity.
Okay, Mbolani, Janet, unmute and submit.
Teacher, 1 kilogram is equal to 10
You are breaking, Janet.
1 kilogram is equal to 10 newtons.
Okay, people, we have a simple formula that weight, 0 is equal to M. mg. That's where people repeat that 1 kilogram is equal to what, but that's the formula that helps us. So I just multiply this by acceleration due to gravity, and then I'll have the weight, okay? Which is our weight, W. So the distance, now, one thing we are going to be very, very specific about in moments is the perpendicular distance from the line of action of the force. We are going to get to this. So the line of action of the force is that imaginary line that passes through the force, okay? And then the turning point is also very, very important, where that force is turning the body from. So the distance, the perpendicular distance between the turning point and then the line of action of the force, in this case, we are calling it D1, okay? So in this case, our anti-clockwise moment, as we see the notes, anti-clockwise moment, we are going to get it as, we get the force, that is M1G, positives in newtons, then times the distance D1. We are going to get to this. Today, actually, in this particular section of our lesson, we just want to understand what is an anti-clockwise turn. An anti-clockwise turn is one caused by a force that turns the body about this point in an anti-clockwise direction. When you look at the clock, this is what we call anti-clockwise. That is the most important thing we need. This one is going to come. We may not pay much attention to this. It's going to come. Now let's go to the clockwise turn. Clockwise turn. We want to come back to our illustration, and this time around we want to put the duster this side. Okay, Mr. Sanjeva has brought a mass. These are some of the masses we use in the physics lab. So we have a mass. We are going to put it there, okay? And the question is, if I release this ruler, I'm supporting it this side. If I release it, where will it turn? Where will it turn? So when I leave it,
So it will turn clockwise.
In a clockwise direction.
So that is another direction we need to understand. A clockwise direction is as a result of when a force turns a body in the direction of the clock, okay? So we can quickly sketch also that. It's our second diagram in the notes. These are moment things. Let's first ignore them for now, and we concentrate on this understanding what a clockwise turn is and what an anti-clockwise turn is. So if you go to our notes, let's draw that diagram in our notes. I believe people left spaces which are meant to be filled.
Oh, you have different notes.
Oh, it's okay, but the concepts are the same, okay? Okay, so this time around our mass is, this side you can call it M2. So when it acts on this stool, its force will be acting downwards. That is M2G. Then we always have a perpendicular distance from the line of action of the force, the turning point, which you can call D2. So in this case, this force turns the body in a clockwise direction. So that's what we needed in this first part of the work, to know what is a clockwise turn, what is an anti-clockwise turn. Any question on that before we go to the next section of our notes? And this is very important in the calculations when we get there. So let's try to understand these bits. Okay, let's draw. Let me share the notes so that you can be drawing those diagrams straight from the notes. And then, so this is our first diagram. And then that is the second diagram. Okay, let's draw quickly. You have 1 minute, and if in case there is any question, someone can ask about what you have just gone through, but it seems to be straight forward.
Now, which one do we draw?
Both.
Both. The one for
anti-clockwise and clockwise. I hope you can see the notes.
No, the one for the notes or the one you have drawn?
Draw both.
You choose.
Okay.
Draw the ones in the notes, the ones that you see on the notes now.
Yes. If you already have them, it's very fine. Okay, we need to move on. I believe we are through.
Teacher, please explain again how we got M1G.
How do we get, if you have mass in kilograms, we you know, there's this formula in this one. We looked at W is equal to mg. It always converts from kilograms to newtons, okay? So if you have any mass, you can always convert it to newtons by multiplying by acceleration due to gravity. So that's how we end up getting mg. Because we are talking about forces, so we deal with forces.
Girls, when you are talking about, in your notes, you have F1 and you have F2. If you look at F1 and F2, they are represented as the product of the mass and the gravitational acceleration. That F1 and F2, in actual sense, are the weights of that mass. But here, because we are going to be using the word force, remember weight is a force exerted by a body on anything that really supports it. So instead of using the word W, in the notes we are using the word F to represent force. I hope that is clear. A force is always a product of a mass and an acceleration.
Ayoki Johanna, you're saying in the chat, can we use W is equal to MA? That one is in topic called motion, where small a is linear acceleration. That is acceleration on the ground.
And we don't use W, we use the.
And in that case, we use F, not W.
F is more, I mean, it refers to forces, F, but W in most cases used to talk specifically about weight. But force covers both weight and any other force applied. So that's why in the notes we are using the word F, or we were using the symbol F to represent force.
Okay. So it means when they ask, does that mean that when they ask you to find change from kilograms to newtons, you have to say F is equal to mg, not W is equal to mg?
But let me ask you something. They cannot ask you to change from kilograms to newtons. They can't ask you to do that because those are physical quantities. However, they can tell you what is the weight of a 1 kilogram mass. That is the more applicable question. So they ask you what is the weight of a 1 kilogram mass, so that you get the weight as a product of the mass and the gravitational acceleration. I hope you understand how I phrased the question. Because
yes, teacher, I understand, but according to I understand. I was just asking, if they ask you in reference to the forces, do you give the what is it even called? Do you say F is equal to mg?
Your problem is this 1 kilogram, its equivalence, or what weight can it exert as a force? Is that okay? So that's what they're trying to actually, the sign you should be using is equivalence, because not equal to, because when you use equal to, it will get weight. 1 kilogram mass will exert a force of a weight of 10 newtons. How does it do that? You, Mr. Salim, go. F is equal to MA. In this case, okay, it is W weight. Weight is equal to mg. So usually this is mass, which is 1, times 10, which is the gravitational acceleration. And that's how we get the 10 newtons. Okay, can you see now?
Yes.
Out what a mass of 1 kilogram. Do you see this mass?
Yes.
It can exert a weight, and the weight it exerts is given as a product of mass times gravitational acceleration. So it is 1 kilogram times the gravitational acceleration, which is 10, and therefore the weight exerted by a mass of 1 kilogram is 10 newtons. Is that okay, people?
Yes. Yes, teacher.
That is the meaning.
Yes.
Okay, friends, let's progress from there. Try to understand. I thank you so much for the questions, because this introduction is very key to what we are going to go through. Okay, so let's quickly read through an anti-clockwise turn. That statement, someone quickly tell us in this. Okay, what you have just done, a meter rule is balanced on a knife edge. Can someone quickly read for us and we move on?
In both cases,
a meter rule
can I read?
Yes, a meter rule is balanced. The notes on the screen.
In both cases, the meter rule turns about the knife edge. In the first case, the meter rule turns in the anti-clockwise. In the meter rule turns in the clockwise direction.
Thank you so much. So F1 and F2 produce a turning effect on a meter rule about the knife edge. That's what we saw. And now that brings us to the fact that the turning effect of a force about a point is called moment of a force. That turning effect, when you turn a door, closing and opening, like today we saw these masses were turning the ruler, it's what we call the turning effect of a force. And this moment depends on, we've seen the force applied is very important. The force applied, and then Roman 2, the perpendicular distance between the turning point and the line of action of the force. I want to repeat that using these very diagrams we have. Okay. So, all right, so looking at the chalkboard, if I have my meter rule,
We are not seeing.
Okay, let me adjust the camera. Okay, let me unshare such that
excuse me, sir, I'm sorry to take you back, but I haven't understood.
you need to be specific, Paula. I don't know what you haven't understood. We've
I
said so
haven't
many.
understood the diagram, so I don't understand.
It's what we are going to be going through, because we looked at clockwise, anti-clockwise. Be specific. If you
Both of them, the anti-clockwise and the clockwise.
The network wasn't on, just be honest and say I haven't gotten this or this, because we haven't spent a lot
So I
of time
haven't
there.
understood the clockwise and the anti-clockwise one, so.
Clockwise is where the clock goes.
You understand it in this diagram I'm going to use, because I'm going to re-explain it. Okay? All right, so we want to understand what moment of a force is. So I'm going to re-explain it. So in the first case, we add a force at this point, okay? And that force was F1, okay? And then we have our turning point where an FH is, okay? So now the line of action, I want us to understand two things in this case. Something called a line of action of the force. So the line of action of the force is this force line. We can talk of as an imaginary line that passes through the force. Is what we refer to as the line of action. So this is our weight or our force acting downwards. Then there's what we call the turning point. This turning point, okay? So this is the line of action. Line of action of the force. And then the next thing I want to talk about is the perpendicular distance between this line of action of the force and the turning point. that perpendicular distance, which you can call D1. So this, you realize that this distance is perpendicular to the line of action. This is the 90 degrees. Okay? So we are referring to this as the perpendicular distance. Speak these words very well, because they are going to be very important. The perpendicular distance. It's not just a distance, but it is perpendicular distance. And it's from the pivot. This can be called, from machines, this can be called the pivot or the fulcrum, okay? So it should be.
We are not seeing.
Pivot
too.
Okay, so this is the. So the perpendicular distance from that. Yes.
I'm not seeing.
Your goal is on.
How is that?
So we can see.
Okay, thank you. So the perpendicular distance from the turning point, which we are going to be referring to as the pivot. Yes?
I'm not seeing the board like.
The problem is with
Teacher,
you.
It's with you, it's not with teacher. You help
it was
yourself.
better before. Those people have network issues. Michael.
Click side to side speaker.
Okay, and share.
Just because not.
We can share the notes such that you people can see what is on the board.
Is that better now?
Yes.
My teacher.
Who is not seeing?
Teacher, you can continue.
So I want us to, I'm emphasizing these key terms. We are finding the definition of moment over force. The very first term that is very important. Okay. We are repeating this such that everyone can be able to see what we are talking about. Okay.
Okay, let us go slowly. Girls, do you see that?
Yes.
This is our people.
Yes.
Explain. And as he explains, he's going to draw. But you also watch what I'm doing. Now, we have, what is that? What have I placed on the pivot?
A meter rule.
Meter rule.
Meter rule.
Meter rule. That's what Mr. Sal is drawing.
A meter rule.
Now we also want to complain. Some of you have very many noises at the back. Now, what has Mr. Sally drawn? He has put an arrow. Do you see the arrow on the board?
Yes. Yes.
Arrow represents force. Represent the force. Mr. Sally draw the force. So when you're drawing diagrams, now let me put on the diagram and you see the behavior. For me, I'm not going to have an arrow, but what have I put on the meter rule?
Mass.
Now I'm supporting this meter rule. Suppose I released it, what will it do?
It would draw.
To move in an anti-clockwise direction.
It is turning out together. It is turning about what point?
About the fulcrum.
At the pivot, isn't it?
Yes.
Turning is occurring at the pivot. This is segment of the pivot at the top there. It is actually the sharp point. Yes, that is our pivot. Is that clear, girls?
Yes.
So, yes. In reality, do you see any line here on this on the meter rule?
No.
Do you see
No.
No. So how do we represent that? in our position, because there's an effect of turning, in physics we represent it that the ruler is going to move downward. That's why we have a downward arrow. Do you see that?
Yes.
Yes.
And so that line which he has drawn is what we call the line of action. Mr. Sali, draw the line of action. So that line is called the line of action. Okay. So, however, in reality, we don't see it. We just see what the force has done, isn't it?
Yes.
Okay. Yes. So in our diagrams, we represent them. Now, we have a pivot. Remember, there is a pivot here. There is a line of action at that point. So we are going to be interested in a certain distance. How far away is this force from the pivot? Are we together?
Yes.
Is the line of action from the pivot. And when we are drawing this distance must be measured starting from where?
From the pivot.
From the turning
Point.
for the pivot. Are we together?
Yes.
Yes, teacher. But how far, we don't just measure how far, we measure the distance such that it is perpendicular to the line of action. So Mr. Sal is going to demonstrate that on the board. Anything that is perpendicular to a line makes what angles with that line?
90 degrees.
Right now. Do you see the symbol for the degrees?
Yes.
So Mr. Sal is going to label that distance now. That is the distance we measure. So that distance is measured from what point?
From the pivot.
From the pivot to the line of action.
The line of
action. Which is where?
The line of action.
Until it reaches the line of action. Very good. I hope now we understand what you're talking about.
Yes.
Teacher.
Thank you,
Okay.
teacher.
So now Mr. Sari, please can help us understand.
So thank you so much, Mr. Sanjay. Now that brings us the definition of moment over force. Moment over force is the same as turning effect over force, but we use this word moment of a force. Now what you want to define, it is the product. We use the word product. It is the product of the
force.
I think from the
force. Distance.
It is the
product of the force
and the perpendicular distance.
And the perpendicular distance
From the line of action.
The line of action to the force of the point.
To the force of the point.
So that's what we define as force times distance. But in our mind, we know that this force is the weight that is acting on the ruler, and the perpendicular distance should be from the line of action of the force to the turning point. That is moment over force, and it brings us to that formula, okay? And moment over force is also a vector quantity. And someone remind us what a vector quantity is.
What is a vector quantity, girls?
Anyone with an idea?
Both magnitude and direction.
Yes, where we get that direction?
Okay, now you told me direction. Do you see the ruler again?
Yes.
So what is the direction?
Anti-clockwise.
Now we are going to repeat this.
Mr. Sanjay, before you go from anti-clockwise.
Before you go to
depends. Paula, are you in? Paula, may you get in? I want to address your question. Paula, open your microphone.
Yes, I'm here.
Anti-clockwise direction is when the ruler turns in the direction. When you look at the clock on the wall, there is where those ants, the direction they are taking is clockwise, and then the other one is anti-clockwise. So when the force turns the ruler in that direction, which is anti-clockwise, it's what we call as it's what we call the anti-clockwise turn.
Okay, so now please may you explain the formula down. I don't know if it's a formula.
Force times distance.
It's from the definition of moment over force. Someone read that definition. Let me share the screen back. Apollo, it's what we have just gone through. May you read for us that definition? Paula, read for us that definition.
Moment over force about a point is the product of a force and the perpendicular distance from the point to the line of action of the force.
So the force is what you've talked about. The word product means multiply, okay?
No, sir, not that one.
Which one?
So when they've just drawn the diagram you drew, there's something down saying if F1 is equal to M1G.
Force is the weight is related to the mass by this formula. It's Ernest one concept. Weight is equal to mass times acceleration due to gravity. So
then what is the one, the F1 and the M1G?
Force acting. Did you start the lesson with us?
No, sir, I had a network issue at the beginning.
F1 was the force one. The mass was mass one. They're just labelings. We add those. You have the notes, and they are very clearly indicated. And then the acceleration to gravity. So it was how we came up with that. It was a force that was turning the ruler in that direction. Then we went in the second diagram. Then we add F2 equal to M2 times acceleration to gravity. That's how it came about, Paul.
Excuse me, teacher.
Yes.
Yes, sorry to cut you off. I just wanted to know what vector quantity is. The definition.
Yes, someone was going to tell us what a vector quantity is. Okay.
What magnitude?
Okay, we are going to look at vector quantity.
That have both magnitude and direction.
Thank you so much. We are going to look at this list 3. We have a scalar quantities and vector quantities. A scalar quantity is defined by magnitude only. Vector quantity is defined by both magnitude and direction. We shall look at it in details as we move on, okay? So since moment over force has a magnitude when we calculate it, and also has a direction which is clockwise or anti-clockwise, hence a vector quantity. Mr. Sonyo is going to help us know what a clockwise is. The direction is
okay. Girls, you remember the turning? What is the turning? We have applied. By the way, let me first ask somebody who is asking about this product. Can you see what is on this? Can you see the reading? Anybody who can tell me what the reading is?
1,000 meters.
1,000 meters.
1,000 meters.
So
1,000 meters.
1,000
grams.
100 grams.
100
like 70 grams.
100
Now, it is
okay. Enough.
Grams is a measure of what unit. It measures what physical quantity. Mass. Our definition does not talk about mass. Listen, guys,
Can we listen?
We're not paying attention. Our definition
What it is doesn't make it towels. Those towels be like
okay?
And like
Yes.
Girls, give an answer only when you put up your hand. We are causing a lot of noise.
I'm given the unit for mass. Please don't shout. That is not Gayaza like.
Put up your hands before you say.
Gayaza girls, we are disciplined. Okay. So what is this unit for? They see them. That unit we have said is for mass. Now remember, that if we are talking about a force, Mr. Sadi, please help me. A force is given as the product of, yes, they can see. A force is given as a product of mass and the gravitational acceleration. So what was the girl's name again? Polar, please. That's why we say that we are using masses, but is in the topic we are talking about, it is talking about forces. So the masses we have been given, we have to get their equivalent in terms of forces. And that's why we get the mass, we multiply it by the gravitational acceleration, so that we can use the appropriate, according to the statement, appropriate quantities that are being talked about in the topic. So if we are using masses, then you have to convert them to forces. I hope we are clear, people.
Yes.
Yes. Okay, so whenever we are given masses, use that formula, convert them to forces, so that you get the appropriate. You can use this formula properly. Now we are talking about, I hope that is clear. We are talking about which direction, please. Remember, girls, what was that direction?
Anti-clockwise. Anti-clockwise.
So, and the turning is specific. When I put a mass on that side, it is not going to turn in another direction. It has a specific direction, and that direction is anti-clockwise. Now we are changing this mass and putting this way. So where will be the turning?
Clockwise.
Clockwise. Is that okay? So do we have a direction? Do you see that the forces are acting in specific directions?
Yes.
Yes. Anything that has the magnitude and direction is called
A vector quantity.
Now we understand
magnitude.
That a moment is a vector quantity.
Yes.
Yes.
So moments are vector quantities because they have both magnitude and direction. I hope that is clear, and it's also clear to whoever has a question.
Yes.
Okay.
What is magnitude?
Excuse me, teacher.
Magnitude.
Magnitude is size.
Answer that question. One of you is given opportunity to answer the question. What is magnitude?
Magnitude is size.
Size. Can you give us a magnitude?
Force, displacement.
I not give us just an example. Just an example of a magnitude. Just magnitude. Give me what, when I say it is size, you just tell me something that represents size.
10 centimeters.
The value. Altogether, you have given me the value of 10. That is the size. Altogether, now, you do this 10 meters east. Suppose I say 10 meters east. Do I expect you to go to the northern side? No. So what is your magnitude?
10 meters.
What is your direction?
East.
So that is now a vector quantity. And what is the name of that distance? Displacement. Altogether, you are displaced 10 meters away in the eastern direction from your original position. Altogether, that's what we mean. So whenever you have something attached, value and direction, then that is a vector quantity. So here we are going to get values, but we are also going to attach anti-clockwise or clockwise. Is that clear?
Yes. Yes. Teacher, but I don't think it answers the question of magnitude.
Just giving you what magnitude is, the value.
Thank you for answering the question.
Oh, hey, thank you.
Okay, our friends, let's conclude this with the S sign of a moment of a force. The S sign of moment of a force. Let's conclude with this. Today it was an introduction, and whoever has understood this, then the next lesson will be much more. Okay, what S sign looking from our formula, force times distance. Give us the S sign of moment of a force.
Newton meter.
Wonderful. Newton Newton meter. That is the SI unit, and in brackets, when you are in calculations, we expect to use the symbols. And Newton is capital N because it is after a human being, and then meter is small. So Newton meter is the SI unit of moment over force. So that's what you've been able to learn today. Unless there's a question, we would love to stop here because it's already lunchtime. Any question before we close?
No, thank you, teacher.
You're welcome.
Yes, teacher, I was asking that is the gravitational acceleration given in the exam, like in an exam?
Yes,
Is it given?
it's always given, and it's 10.
Okay.
No, always.
It's always given, it's a constant.
But if it's not given, we use it.
Yes, you use it. You need to know
You
it.
should know it.
Excuse me, teacher.
Thank you, teacher.
Thank you, teacher.
There's someone else.
Thank you, teacher. Hi, Patricia.
Please leave your colleague to ask a question.
Teacher, can you write the SI unit in plural form?
In plural?
Meter, not Newton's meters. We are carrying.
Okay. Thank you, teacher.
Bye, teacher.
Bye, teacher.
Bye. Enjoy your
Bye,
lunch.
teacher.
Thank you for teaching.
Bye, teacher.
Nice weekend. Thank you for teaching. Bye.
Thank you, Mr. Weekend. Thank you, Mr. Sanjay. Thank you, Johanna.
Tomorrow. Bye.
Yes, there's a seminar.
Seminar tomorrow. Please send the link of the seminar.
Hey guys, I hope you love
The seminar every Saturday.
The seminar is every Saturday.
Seminar. Bye. Thank you.
Bye.